Welcome back. My name is Pi, and today I'm going to talk about a function that I wrote in MATLAB. We're going to talk about direct single shooting today, and I hope you watched the previous videos because it's going to be very helpful in order to understand this video. Okay. Here you go. Let's start with some API. You should be able to get this piece of code from GitHub. The link will be added soon. And you need MATLAB to run this. So we have everything running. You can do it along with this video. Let's type help direct single shooting. Okay, you see all this help text. So direct single shooting solves a given optimal control problem using direct single shooting method. It will return capital X, okay, which is the discretized state trajectory. U is the discretized control input trajectory, which is the optimal one, is the one that we already solved, and T is the time vector, and J is the optimal cost. Okay, so you can see it here, X, U, T, and J. Okay, direct single shooting take lots of variables, so you have to pay close attention to this. So capital J or J star is the minimum values of integrated Lagrange term from 0 to capital T plus the major term evaluated at the final condition X of capital T and the final time T, or capital T in this case. Notice that you have this capital T here and you have this capital T here. This expression is based on the one from the books. They use capital T. Here is supposed to be lowercase t, but according to MathWorks convention, this has to be capital. So can't do anything with that. All I can do is to change this capital T to TF later. Okay, I will change that later in the code. Even in the help text, I change that to TF. Okay, U star is the optimal control policy such that you get this J star. Okay, all this stuff are subjected to all these constraints: dynamic constraints, path constraints, terminal constraints, and final condition x of 0 equal to x0, and these states have to be given. Okay, and everything is mapped out. I even say what kind of what type of data you need to put in a function. So notice this API Lagrange measure F, all these capital letters, they are stated here. Okay, so Lagrange term, okay, has to be a function handle, and most of this stuff is function handle. So Lagrange term is function handle that take x, u, and t, and this should return you a scalar value. Okay, the measure term is also a function handle. It should take xn, which is the final condition, and final time tf. Entire expression should return you a scalar value. For dynamic system, okay, f takes x, u, and t, and it should return you derivatives, okay, of the states, and that has the same dimension as the state x itself. Okay, all these constraints have to be written into function handles. Okay, all the path constraints have to take x and u as parameters. Okay, and the terminal constraint should take xn and tf, which is the final condition and the final time, very similar to measure term. Okay, initial states, okay, has to be given. Yeah. The final times is now called TF. Okay, it's positive infinite scalar or empty. This implies that if you don't know the final time, you can leave it as an empty matrix. For example, you might have minimum time problems and you don't know what will be the minimum time. You want to simulate to that particular minimum time that you don't know. and this will definitely solve TF for you, okay, even though you don't know the final time. The next thing is number of sample, capital N, and this depends. You can make N equal to 100, so you can make it equal to 10. It depends on what you want. The greater the numbers, the more accurate it is, but more time it took to the more time it takes to compute entire optimal control trajectory. Number of control inputs is M. This one have to correspond to this U here and this U here. So anywhere that have U must have the same dimension as M. For example, if my control input has 2 signals, then I need this M has to be 2. And the last thing that we have to specify is the integration method. Okay, you should be able to specify whether or not you want to use Euler method or fourth order Runge-Kutter's method. Okay, of course, Runge-Kutter methods is more accurate compared to Euler, so most of the time I use RK4. Okay, done with API. Let's look at the example. Okay, the first line is clear all. Okay, so don't call this if you want to keep something in your workspace, because it will clear everything from your workspace. So I can skip this line. Let's look at the Lagrange term. I declare it as an anonymous function to take x, u, and t, and it should return u square. And all this stuff I forgot to mention, by the way. All this stuff are based on the previous examples on the precision table, my double dot equal to negative by dot negative ky plus u. So keep that in mind. So the Lagrange terms, okay, is equal to u square. The Mayer term is 0 because we don't have any Mayer's term. All the parameters, mass, damping, and spring constant, I define them here. Okay. F is the function, is the dynamics. So we solved that already. It's based on the state space formulation. The things on the top is x2. I use x parentheses 2, which means the second state of x. And I have negative k over mass plus x1 multiplied by x1 minus b over m multiplied by x2 plus 1 over m multiplied by u. You can see that the dimension of this matrix is 2 by 1, which is the same as dimension of x. Okay, constraints, they all have to be in terms of function handles. So the path constraints must take x and u and return something. So for equality path constraint, I remember that we don't have any. So I set this one equal to 0. Same as in inequality terminal constraint, I remember that we don't have any. So even though it taken these variables, but you don't have to put anything inside. Okay, if you don't have any constraint. So we have inequality path constraint, say that x1 or the position has to be less than 7. So therefore x1 minus 7 has to be less than or equal to 0. Also x1 have to be greater than negative 7. That is the same thing saying that negative x1 minus 7 is less than or equal to 0. Then you just stack them together like this, one on top of another. Then you will have inequality path constraint. For equality terminal constraint, it should take the final condition xn and the final time tf. Okay, but the expression itself does not need to contain any of these parameters. I stated here as xn minus 0, 0 has to equal to 0. This means that xn have xn, which is the final state, have to go to 0. Okay. So next step is the initial condition. Okay, the position start at 0. The position start at 5. My bad, and the velocity start at 0. The total time is 2. Okay, and the number of samples is 20. The number of control input signal is 1 because that's based on state space formulation. U has the dimension of 1. Okay, so this should be easy, right? Whereas you have everything, and you say that my integration method is RK4, and all you have to do is to run this piece of code, direct single shooting, that take Lagrange Meyer F, all this stuff, and you run the script. Control Enter. In a matter of seconds, it's solved. Okay, so you got this trajectory, state trajectory from 5 to 0 within 2 seconds. Okay, and the velocity go from 0 to 0, so that's good. And the control input trajectory, it might seem continuous, but it's actually a bunch of lines connecting 20 dots together because we have 20 samples. Okay, cool. So you can actually type out this X because it's a script. So notice the initial state start at 5 0, and at the end it end at 0 0. Okay. Also notice that you have 21 column in total because you have the initial states and then 20 sample after that. So it's 21. If you type U, capital U, you see that you have 20 control input. Okay, because it doesn't matter what the final input will be. It won't affect the final state. It will affect the following state, but not our concern. So that's our U, and you can type T. T is the time vector from 0 to 2. Okay, you have 20 samples plus the initial time 0, and optimal cost 15.8031. Okay, let's look at another example, a very similar one. So this one has similar cost, U transpose multiplied by U. In this case I want to make it generic, that's why I wrote it like this. There's no Meyer term, and the dynamic system is a bit simpler. I just use spring mass system without the damper. Okay. But the constraint, I change the inequality path constraints so that my U, which is the control input, is bounded between 2 and -2. Okay, so I have this U max, which is the maximum saturation point, and then if you do the math, you should be able to get the same expression as well. So just take a look at this and just think of it as a side exercise. Just do it on your own. Okay, everything else is the same. I want the terminal condition to be at 0 0, but my initial condition is changed from 5 to 0. Now it's 10 and 0. TF is the final time. I changed it to 10, and I bumped up the number of samples, which is 20 before, which was 20 samples before. Now I have 40, and number of control input signals still the same. Method is RK4. Now we are ready to run. If you notice, it takes a bit longer because the number of samples is more. Imagine you have capital N equal to hundreds, it would take so long. Now we get state trajectory, and you notice the color is different. It will be different every time. I wrote the code such that the color will be different, depends on number of states. So you have 100 of them, none of the colors should be the same as well, and it shouldn't be doesn't matter. So let's look at the state trajectory. 10, it could start from 10 and it go to 0. Okay, within 10 seconds. Okay, the velocity go from 0 to 0. That's fine. And if you look at the control input trajectory, you see that the the trajectory is bounded between 2 and -2. Okay, so that's kind of cool. So let's look at U, and if you notice, you see that none of this control input exceed 2 or -2. Okay, so thank you for watching. I hope this video helped you understand my code, and all these examples should be straightforward. You should be able to run it, without any problem. And thank you for watching again. If you have any problem, if you have any controls problem you want me to formulate for you, or you want me to run it in the program for you, and please let me know. If the program has any bug, then definitely let me know. Okay, thank you again, and keep in touch.